Good morning and welcome to this next lecture on sound and structural vibration. We were looking at how a panel vibrating in a single mode changes its nature with respect to the frequency at which it is vibrated. Okay, so a mode of this form V tilde PQ sine p pi x by a sine q pi z by b is driven at this omega. Okay, so we are looking at single mode vibrations at single frequencies. Okay, and very specifically we keep the amplitude a constant. Okay, for those who are aware of vibrations of plates and shells, the amplitude has this sort of a term in the denominator, omega square minus omega square pq, and as omega the driving frequency changes and gets close to the resonance, you will have amplitude increased, or as it moves away you will have amplitude decrease as a function of frequency, but that's very non-linear. So we don't want to bring that aspect in, and we are just understanding the cancellation effect. Okay, that's what we are doing. And so throughout this discussion V tilde PQ has been held a constant. Okay, merely change in frequency is affording us cancellations or lack of cancellations. So we started off with this plate over here, case 1 at very low frequencies. Okay, so there is this panel which I have drawn. You can take it more rectangular, A is bigger than B or B bigger than A, and at very low frequencies Kx overwhelms K, Kz overwhelms K, and therefore there is very heavy cancellation and only the corners remain uncancelled. Okay, so it's a poor radiator. So that same mode remains the same, but due to the frequency of excitation it is now a corner mode, only the corners radiate. Okay, in the beginning we had seen a case where the entire panel is equivalent to one cell. This is that case. Okay, 4 quarters make one cell. Okay, now as frequency increases it is possible that Kx is greater than K, but Kz becomes less than K. It's possible. Okay, in which case lambda x is less than lambda the acoustic wavelength, and lambda z is greater than lambda. Okay, so then what happens, I'll keep the same colors. So then this panel has cancellations along the x direction. Okay, so what happens is we end up with two regions, strips actually, along the z direction which remain uncancelled, and this is called the z edge mode. Okay, now it can also happen that Kx becomes less than K, okay, and Kz is above K, in which case lambda x is greater than acoustic wavelength, lambda z is less than acoustic wavelength. Can also happen. based on dimensions, okay, based on the relative size. P pi by A is x wave number, q pi by B is z wave number. So, one relative to the other based on dimensions and mode number. It could happen that we are presented with this situation as frequency increases. Then what happens is that we have X edge modes. Two strips of this sort remain uncancelled. Okay, these are X edge modes. Okay, following this, we can have the next situation, okay, where kx square plus kz square is greater than k square, but kx is less than k and kz is less than k. Okay, this is a unique situation. Okay, so lambda x is greater than lambda and lambda z is greater than lambda, but not totally. Okay, there is not a total so what happens here? Here we will get double edge modes. We get an edge here, we will get an edge here, we will get an edge here, and we will get an edge here that are radiating. Okay, so these are called double edge modes or XZ edge modes. XZ edge modes, XZ edge mode. Okay, and lastly what happens is that k square is greater than kx square plus kz square. Okay, and k is greater than kx and k is greater than kz, at which point the full plate is radiating. No cancellations now. And radiation efficiency reaches 1. Okay. One more way of looking at it. Okay. So let me draw the picture first, or let me do this derivation first. So we have the full plate equation, okay, the full vibrating plate equation. It's given by, let's say, d del 4 eta del x square, del x4 plus twice del 4 eta del x square del z square plus del 4 eta by del z4 x comma z comma t plus mass per unit area del 2 eta del t square equal to 0. So this can support the wave eta x comma z comma t in the form some amplitude e to the power of j omega t minus j k x x minus j k z z. Okay, so if we substitute this in here, I'll get a d a, okay, 4 derivatives gives me kx fourth, okay, plus twice two derivatives in x gives me minus j kx squared, two derivatives in z gives me minus j kz all squared, okay, into a again plus a into kz fourth. Okay, the propagators I am keeping outside, e to the power j omega t minus kx x minus kz z, I have kept it outside. Okay, and then the time term gives me minus m omega square a e to the power of whole stuff equal to 0. So this propagator I can cancel from both sides, the amplitude I can cancel, okay. So this gives me d kx fourth, this minus squared and j square goes, so I get plus 2 kx square kz squared plus kz fourth, okay, which is equal to d kx square plus kz square whole square is equal to m omega squared. Okay, so if I carry on here, I get d, or I get kx square plus kz square whole squared is equal to m omega squared by d, and if you recall, this is actually kb fourth, okay, the free wave number in the plate, free wave number in the plate. Okay, that means what? I have an infinite panel, I have an infinite plate that goes out to infinity, okay, and somewhere locally far away I have given a local excitation, as a result of which wave numbers are propagating, okay, and that at omega it is this kb fourth, it is kb fourth, okay, that is the free wave number in the plate. Okay, now because it's a rectangular plate, you can have it in two components, so you can have kx square plus kz square is equal to kb square. Okay, kx and kb are unknown, they can be any combination, they can be any combination based on whatever boundary conditions, etc. But the square sum is kb square. Okay, so this is one bit of knowledge that we need. Okay, then it is also true, another equation is also true, that if my kx is equal to say p pi by a and kz is equal to q pi by b, now we are on to a finite panel. These are the modal wave numbers kx and kz. Okay, then p pi by a whole squared plus q pi by b whole squared is equal to omega pq square root of m by d. Okay, this is also true. So this is the equation for pqth mode resonance in a simply supported plate. Simply supported plate. Okay, so we will see the meeting point of these two equations. We will see the meeting point of these two equations. Okay, so let us see now. So I have a space, a wave number space. Okay, let us say, let me make it here. Okay, so this is x direction. Along x direction I will choose pi by a, 2 pi by a, 3 pi by a, 4 pi by a, 5 pi by a, 6 pi by a, 7 pi by a, etc. Okay, these are x wave numbers. Then let me choose this little oblong. Okay, so I'll choose here one line here, next line here, next line here, next line here, next line here. They are supposed to be equidistant and so forth. Okay. Okay. What is this? This is pi by b, pi by b here, 2 pi by b, 3 pi by b, 4 pi by b, 5 pi by b, 6, 7, 8, 9, etc. Okay, this is in the z direction. Z direction. Now what do these represent? Each intersection represents a mode. This is wave number space, okay? But each represents a mode. Each of these blue dots is a mode. Each of these is a mode. Okay. So now what I will do is I will draw the acoustic circle. Acoustic circle. Okay. So let me draw the acoustic circle. Acoustic circle, let's say, goes like this. Let it go like this. This is the acoustic circle. So let it go vertically and it is turn horizontal. Okay. Okay. Hold on, hold on. I'd like it more representative. Let's see. I'll like it more. So let's do this. Takes off vertically and comes off horizontally. Okay. This is the K circle. This is K, acoustic wave number K. Okay. And let me draw these vertical lines. Let me draw these vertical lines. Okay. Now, corresponding, let's say this is omega, corresponding to omega 1, let's say omega 1. Okay. And it's low frequency. Omega 1, it's low frequency. Okay. Now, corresponding to that, we will draw the free wave number line also. Okay. What is that? Let this be the free wave number line. Okay. So let us see. This starts off like this. It starts off like this and goes through this, and it ends up here, let's say. Okay. So that is what, that is the free wave number line, KB line, that's KB circle, KB. Okay. So how to write it? This is K at omega 1, this is KB at omega 1. Okay. Now, what did we say earlier? Earlier we said K x square plus kz square is equal to kb square. Okay. And we also said that p pi by a whole squared plus q pi by b whole squared is equal to omega pq square root of m by d. Okay. And this is also kb squared. It's from the same equation. Okay. What do we mean? At low frequencies, so let us see. Let us write it. At low frequencies, okay. Now Kb is bigger than K, the acoustic wave number. So that's what is indicated over here. Okay. Now, so at this frequency, you can see at this frequency, I wish I had more colors. Okay. Here, what are these? These are p pi by a and q pi by b, which are greater than k. Okay. So these are what? These are corner modes. If you look at the previous picture, these are corner modes. Okay. At extremely low frequency, it would, this red line would have been here. At the starting, this would have been right here. That means what? Let me just say, at not at this frequency, at low frequency, all modes start as corner modes. Okay. Now, as frequency goes up, frequency goes up. Okay. The K wave number goes up, K goes up. Also Kb, which is already greater than K, also goes up. Okay. So at a certain instant we are here, K circle is here, KB circle is here. Now look at this, okay. What is this region? What is this region? This region is where, okay, this height is K, okay. This region is where K is greater than Q pi by B, which is Kz, which means what? Lambda is less than lambda z. What modes are those? Those are the z edge modes. Z edge modes. Okay. So what happened? Whereas when we started, all the modes started as corner modes. Okay. By the time we reach here, K reaches here, KB reaches here, some modes have become Z edge modes. Okay. These were corner modes earlier, now they have become Z edge modes. Now what about this set of modes? Okay. This set of modes is where K is greater than P pi by A, which is Kx. That means what? Lambda is less than lambda x. These are what? X edge modes. X edge modes. Okay. So this region here, above this line here, this is K, okay. This is K. Okay. So this point is KK. This is K. Okay. So these modes are X edge modes. These are Z edge modes. These here are corner modes. Okay. So now there is this region over here where K is greater than P pi by A, it is greater than Q pi by B, and also K square is greater than P pi by A whole squared plus Q pi by B whole squared. Okay, that's what the circle implies, right? So these are acoustically fast modes. Acoustically fast modes. There is no cancellation. No cancellation. No cancellation. Okay. Now what about this small region here? Let me, okay, there are hardly any modes now, but there is a small region here. What is this region? This region is where this holds, okay. K is greater than P pi by A, okay. K is greater than P pi by A, K is greater than Q pi by B, but K square is not greater than P pi by A whole square plus Q pi by B whole square. It's not, it's less, okay. And therefore these are XZ edge modes. Edge modes. Okay. So at any instant you will have all these modes. At any instant in frequency you will have all these modes. Okay. Now I will bring in the idea of a resonance. Okay. If you look at these two formulas, this of course comes from the free infinite plate, free bending wave number, and this comes in from the finite plate. Okay. So this KB line, which is the free wave number line, if it passes through a PQ point, if it passes through a PQ point, that means KB square is equal to this, okay, and KB square is equal to this, and this is equal to this. So this is a resonance frequency. This is a resonance frequency. Okay, that means when this blue line here, which is the KB line, okay, cuts or passes through or near one of these dots, that mode is resonant. Okay, so let me say it and I'll write it in the next page. So you have modes becoming resonant first. Because KB rises faster. Okay, KB rises faster than K. KB is above K. Okay, so as KB moves faster outward than K, it will cross these blue dotted lines. So modes get resonant first and are not are below coincidence. Below coincidence. Okay, so they are not efficient radiators, but they are in resonance. So that does give you some resonant radiation. And let me just tell you that the coincidence frequency for most thin panels is in the range of 6 kilohertz. In that range, okay, it is inversely proportional to thickness. So thicker panels will go down. Of course, thicker panels are hard to excite and are poor radiators by themselves. So we will take 6000 hertz as some kind of number for steel. Okay, so it's mechanically it's very hard to excite that frequency. Okay, mechanical excitations usually don't come up that high unless you have cavitations or explosions or something like that. Okay, so that means what? Most modes will be below coincidence. Okay, but they will pass through resonance. So most radiation is that we will see is resonant radiation below coincidence. Okay, now what happens is that a little later, as this KB moves out, the acoustic wave number line moves in. So then they are no more resonant. They are no more resonant, but they are above coincidence. Above coincidence. Okay, now please don't confuse this coincidence with the coincidence between K and KB. I hope I have made that clear. I will make it clear in a general lecture next. Okay, so this is the plate material and acoustic speed related coincidence frequency. This is the absolute kind of coincidence frequency. But your K, okay, square can be equal to P pi by A whole squared plus Q pi by B whole squared. Okay, that is when coincidence with the mode happens. Coincidence with a mode happens. Okay, in the 1D case we saw what? And K becomes equal to P pi by A. Okay, in the same sense over here. So now the mode was earlier resonant because KB passed through it. Now it is above its own coincidence. So it becomes an efficient modal radiator. However, it is no more in resonance. Okay, so that's how it goes. When the mode is resonant, it is not above coincidence. When the mode is above coincidence, it is no more resonant. Okay, now as time goes by, as frequency further increases, somewhere what will happen is, okay, you will have the actual coincidence. That means the K half circle or quarter circle will be equal, lie on KB quarter circle. Okay, I will show that as this. So both of them come together in one place. So that's actually the coincidence which I am speaking of here. Okay, which is also rare. Now at that point what happens is the modes through which KB line moves are resonant and they are also above coincidence. okay. And beyond that what happens is that you will have k going faster, k starts to overwhelm, k circle starts to overwhelm. So those modes below the k circle are all above coincidence, okay. So all these modes will be above coincidence. So suppose k has moved here, okay, and kb, the plate line, plate quarter circle is somewhere over here, then all these modes are first of all above coincidence, and then some of these modes are resonant also, okay. So this is how the modes behave as a result of change in frequency, and we have brought in the idea of resonance also, okay. So this is a story of panel radiation, okay. Now in the next class I will summarize this idea, and we will start looking at two papers, one by Wallace, the other by G. Majdanek, okay, who gave numerical versus closed form expressions for radiation efficiencies. Radiation efficiencies for individual modes. Individual modes. Of course, finally, Majdanek gave an expression for modal averaged radiation efficiency. When all modes radiate together, okay. Yeah, I should mention one more paper which is by Zai, okay. They also have given numerics, they have given numerical calculations on modal average radiation efficiency. We will see this in the next class. I will stop here. Thanks.